If you've ever written code that runs on hardware, you know that feeling, how quickly things can spiral into a tangled mess. Well, today, we're going to walk through a professional's guide to building embedded software that's robust, maintainable, and actually built to last. Let's get right into it. Everything, and I mean everything we're about to cover, rests on this one golden rule. It's super simple. Clarity comes first. We write clean, understandable code by default. We only start optimizing when we have hard data, not just a hunch that something is genuinely too slow. This philosophy is our North Star. So why are we so obsessed with this rule? Well, it's all in service of these four goals. We want systems that don't just crash for no reason, systems that are secure from threats, systems you can move to new hardware without a massive rewrite, and maybe most importantly, systems that are maintainable, that someone can understand and update 6 months from now. And yeah, that someone might just be you. Here's our game plan. We'll start by digging a little deeper into that core philosophy. Then we're going to build up our system on 3 pillars: the code structure, the tools and processes we use, and its overall resilience. And finally, we'll see how it all pays off in the long run. So let's just lock in this core philosophy one more time. This isn't just some nice-to-have suggestion, it's a discipline. Your default action should always be to make your code readable. Optimization is the exception, and you gotta prove it's needed with real measurements. Trust me, this will save you countless hours you'd otherwise be spending trying to debug some clever but impossible-to-read piece of code. All right, on to our first pillar, architectural structure. This is all about how we organize the code itself to be flexible and tough. And we're going to start with the biggest challenge of all, talking to the hardware. The first big concept you need to know is the hardware abstraction layer, or HAO. You can think of it as a universal translator. Your application logic speaks a really simple language like, hey, turn on the blue LED. The HAO takes that simple command and translates it into the super specific, low-level register writes that your particular microcontroller needs to actually do the job. And working right alongside the HAO is its partner, the Operating System Abstraction Layer, or OSAL. It does the exact same thing, but for the real-time operating system, or RTOS. So instead of your code calling a function that only works with, say, free RTOS, you make a generic call, like create a new task, and the OSAL handles all the specific details behind the curtain. And here's the result. It's beautiful, right? Your application logic sits way up at the top, totally protected by these abstraction layers from all the messy, specific details of the hardware and the OS down below. If you've ever had to port a project to a new chip and it took you weeks, you know exactly why this is a total lifesaver. This is how you get true portability. Next up, modularity. This is really about balancing 2 key forces. On one hand, you want high cohesion inside a component. That just means everything in that module is closely related and does one job really well. On the other hand, you want low coupling between your components, so they're as independent from each other as possible. Nailing this balance makes your whole system so much easier to understand and change. So how do we actually make that happen? Well, first, you hide a component's internal data. Don't let anyone else touch it directly. Second, design the public API, the front door to your component, before you write the code. And that API needs to be clear about how it can fail, not just how it works. Every single piece has to be testable all by itself. And finally, you should be able to turn off non-essential parts without crashing the whole system. Okay, moving on to pillar 2, the development ecosystem. You see, a brilliant architecture doesn't mean much if your tools and processes are a mess. This isn't about the code itself, but the whole environment that helps you create quality code. Now, this is a principle that can totally change the way you work. The idea is that your application logic should run on your laptop just as well as it runs on the actual hardware. Why? Because this lets you develop and test at lightning speed without constantly waiting to flash a physical board. It's a massive productivity boost. Now, to make this work, there are a few things that are absolutely non-negotiable. 1, the code has to build and run on your host PC, period. 2, your simulation setup needs to have complete control over the concept of time, so you can pause it, step through it, whatever you need. And 3, the logic has to be deterministic. The same inputs must always give you the same outputs, no wiggle room. Quality isn't something you check for at the very end, no way. It's a continuous process that's just part of your daily workflow. You use static analysis tools to automatically sniff out bugs before the code even gets merged. And every single time you commit code, a suite of automated tests runs to make sure you didn't accidentally break something. And that brings us to our third and final pillar, system resilience. This is all about how your system, and just as important, your team, handles things when they go wrong. It's about planning for failure, not just hoping for the best. So, I want you to ask yourself this question. When you get bad data from a sensor or a peripheral just stops responding, what happens next? Does your system recover gracefully, or does it just descend into chaos? A resilient system has a plan. It uses the same strategy across the whole system for reporting errors. It knows what a safe state is and how to get back to it. It uses tools like watchdog timers to recover from total lockups. And, this is key, it actually documents how things can fail so you can analyze and prevent those failures in the future. Resilience also means security. And security is not a feature you can just sprinkle on top at the end. It has to be designed in from the very beginning. That means you check every single piece of data that comes from the outside world. Components only get the bare minimum permissions they need to do their job. And please, never, ever hard-code secrets like API keys or passwords in your source code. But resilience isn't just about the code, you know? It's about the people. This principle is so important. If your project grinds to a halt because one person is out sick or on vacation, you don't have a resilient system. You have a huge risk. So, the solution is to actively spread that knowledge around. Try pair programming for the really tricky parts of the code. Make code reviews mandatory, not as a test, but as a way to share what you've learned. And most importantly, document why you made a design decision, not just what the code does. Okay, let's bring it all home. We're going to connect the dots and see how all these principles we've been talking about directly lead to those big goals we set out at the very beginning. Look at this. This is the payoff right here. All that effort you put into layering and abstraction, that buys you portability. The discipline of modularity, that's what gives you a maintainable system. Committing to simulation-first development, boom, speed and quality. And fostering that shared knowledge, that's how you build a resilient team. Every principle has a direct, tangible reward. And at the end of the day, this whole thing isn't about creating some perfect academic architecture. It's a practical way to manage the insane complexity of embedded systems. It's about reducing risk and building a product that can actually grow and evolve for years, not just months. So I'll leave you with one final thought to take with you. Take a hard look at your own projects and the way you work. Are you building something that's designed to be maintained, ported, and scaled for the long haul? Or are you just racing to get it out the door? Is your architecture truly built to last? Or was it just built to launch?